Greetings. In this one we will do an infinite product. And what an infinite product is a similar idea like infinite sum. That means like in an infinite sum we add terms from the first term and ordered by natural numbers 1, 2, 3, 4 until an infinite term. And we add all these up. It can diverge, it can converge, and in case it converges, it will converge as an addition. So in these infinitely many terms will add up to a finite number, then it converges, and you can even sometimes evaluate the convergence very often quite easily. Very often also not that easily. In any case, in this example we will have an infinite product. So the same idea, but it will be infinitely many terms that are all in product with each other, and they will have a finite result, and we want to determine this finite result. So not only do we know that it converges as an infinite product to something, but we actually know it will that it results in something and that it converges, but we also want to know the value of that the exact value of that convergence. So we have an infinite product and it's denoted as capital Pi. That's the way that's denoted. And the usual way that like the thing we will do here is, by the way, a limit of the whole thing, where n is set to approach infinity. And n will be the upper bound, the very last term, because it's an infinite product. It goes from k equals 1 to n, but the n will approach infinity. So we have to write that. And then the arguments will be interesting because it will be in combination with the indexes actually. So that's the interesting thing about this example. So we have the infinite product of k over n to the 1 over n, or the nth root of k over n, as basically the individual terms are called k. That's why k starts at 1 and then goes to n. So it's like k equals 1 to k equals n, if it was to be properly set like very explicitly, so that we are very close to understanding everything. So what I'm actually doing here all along is, not only does it go to the infinite term because I said limit n approaches infinity, but also this n, we could also do infinity here, but I'm just writing the n in both cases for both the upper bound and also this thing that's part of the argument. Both will go to infinity. So we have this. Now, what is the inf? And also this is 1 over infinity. So the infinite root of k over infinity. And the infinite product of that. What is the result going to be? Well, it actually will turn out to be a concrete value. But we will get there with some steps. So there are some very common tricks to use here for infinite products. What it means is, well, this thing will generate, for k equals 1, I will have 1 over n to the 1 over n. For k equals 2, I will have 2 over n to the 1 over n. For k equals 3, 2 over, 3 over n to the 1 over n. And for k equals, for some general k, we have k equals n to the 1 over n. And it goes until k equals infinity, then we have infinity over n to the 1 over n, but n is infinity all along. And then we want to take a product of all these terms, and I say 1, 2, 3, all the natural numbers in between, all the way to the infinite term. And we want to take a product of all of these, and the result will be a convergent finite number. So that's where we want to get. All right. So here I will actually use ideas related to logarithms, because they have an interesting property of how we can change products into addition. So what we will actually use here is a concept that will allow us to use the properties of logarithm. I will use the natural logarithm. How to use that in order to rewrite this infinite product as an infinite sum. I will apply natural logarithm to this expression, and then in the end I will put it as the exponent of e. So I will reverse the process in the end. But by applying natural logarithm, I can use a lot of properties of it that will help me along the way towards evaluating the concrete value here. So if I apply ln, I have to remember that in the end I will have to do e to the what we get in the meantime to reverse the ln. But for now, I will apply the ln and use all the advantages of that. So the idea here is that I can interchange the ln with the limit, first of all, which is a very, let's say, nice property. But actually, when we have a product, once we get the ln here, we actually can put it all the way to the argument and replace this by a sum. So the idea here is that we will have limit n approaches infinity, ln, and then I can still keep the infinite product k equals 1 to n, still n approaches infinity for all of this, k over n to the 1 over n, alright? But then if I want to replace, there's this property right here that says ln of AB equals ln of A plus ln of B. So that means that once I replace this product by a sum, I must have the ln no longer outside, but it must be for each term. So it will go inside. So this will further mean limit, and I still keep writing this limit all along, of a sum, and it will have the same bounds. Because we have still the same amount of terms, n terms, as it goes to infinity, from number 1 to infinity. And now we switch each of the terms, we don't work with them, and we don't put them in product, we will put them in addition now, because of this. This works for an arbitrary amount of terms, as we see. So we can have ABC, ln of A times B times C will equal ln of A plus ln of B plus ln of C, as many terms as we want in that context. So now, this will equal to a sum from from 1 to n, not a product of ln of each of the terms, which is ln of k over n to the 1 over n. And now that we are here, we can further use the properties of a natural logarithm. We still have it there. A property of the natural logarithm that we'll use here is, we can drop the exponent of the argument in front, outside of the logarithm. So if there is an argument of a natural logarithm or of a logarithm that contains a base to an exponent, we can take the exponent outside completely and make it a multiplication or a factor that multiplies the logarithm on the outside. So this is equivalent to rewriting once again limit n goes to infinity and of the sum k equals 1 to n, and this 1 over n will go in front of the natural logarithm k over n, like this. And now this might seem like we didn't get very far. We have transformed a lot of things, we have rewritten a lot of things a lot of times. And one might still ask himself, well, where did we actually get? Did we get any further? Did we improve? This whole thing is now the argument of this infinite series. Just to reiterate our work all along. We've gotten from an infinite product, and by taking the natural logarithm of it, we could rewrite it a whole lot of ways. The biggest idea here was that a product of a logarithm with product of terms and its argument can be written as an addition of logarithms of those individual terms. And that was applied even for this infinite product, infinitely many terms. And now, instead, I apply logarithm, put it inside of the argument, but I will switch it to infinite sum, not a product anymore. That's this trick, applying the logarithm. And namely, we apply natural logarithm with base e, so that later we can write it as e to something, e to what we've gotten so far, to reverse the natural logarithm very easily with this constant. So we got all the way here. And here, we have to realize one thing. It ended up, this example is special, and that's why it also works all along this way, why we can get all the way to this result. The reason this whole thing works is because this is precisely a Riemann definition of integration of ln of x. And how does that work? Well, what this means is that if for a better imagination, what I can also do, I can just write infinity symbols instead of the n's here. Alright, I will just do it. I will just say 1 to infinity. So we're taking infinitely many terms and adding them up of 1 over infinity of ln of k over infinity as k goes from 1 to infinity. So as infinity is 0 all along, so that means that k starts at 1, at 0, and it goes all the way to infinity over infinity, all the way to 1. So ln goes from 0 to 1. And it's the value will go from 0 to 1, and every time it's divided by infinity. Well, this is not a rigorous way to write it. We should keep this way of writing it, alright? So what this means is basically a Riemann representation of an integral, take an infinite sum of infinitely many pieces of the interval. And the interval is cut out for each term, as the term itself goes from 1 to eventually equal to n. That is represented by the k over n in the argument, and then also each value is divided by n. So we get n divisions of the interval, and now I do the limit, so it's like infinitely many divisions. That's why we'll actually replace it by an integral in a second, alright? So that's the That's the truth behind that. So I divide this into n pieces, and each piece will gradually increase from 1 over the amount of pieces to the amount of pieces over the amount of pieces. That means to 1 unit. So this can be by Riemann definition, infinite sum definition of a Riemann integral can be rewritten. This thing I can write as the integral from 0 to 1, that was the 1 over infinity to infinity over infinity, so 0 to 1 of ln x dx. And now I can use integration by parts to integrate this. And when I get the result, I will evaluate it at 0 and 1. And that will precisely be our result, that we will only need to exponentiate. And during the exponentiation, after the exponentiation, we really get the value for this infinite product. So, I mean, I have the calculation done for this one, but I mean, we can still do the integral. It doesn't hurt. So ln of x dx, I can also imagine it is 1 times ln of x. I'll use integration by parts, and I will say this is u, and this is the derivative of v. And so, actually, this is v, and this is the derivative of u, like two functions, u and v. U is the 1, u prime is 1, and v is ln x, some imaginary u and v. That's how integration by parts works. I'm not going to go into deeper details in this one. Alright, then it should equal to uv minus u times v prime. Well, that will be x times 1 over x. Well, actually, ln x, that doesn't change. So times ln x, ln of x, minus integral of 1, so that's integral of x times derivative of ln x times 1 over x dx. Well, that is x ln x minus x. Alright, here's 1 integrated to x. It should be this evaluated 1 and then 0. So it's 1 ln 1 minus 1 minus this evaluated 0. So 0 minus 0 actually. So ln 1 minus 1. And all of this, by the way, is minus 1. Alright, so this is my result for the integration, for the integral. And now, at the very end, what I can do is go back. So what I did, how did I start solving the thing? I had only this thing, and I applied natural logarithm. Now at the very end, I got that all that is equal to minus 1. I have to exponentiate it. So the result of this thing is minus 1. Minus 1. But if I want to remove the fact that I caused the natural logarithm, that I added the natural logarithm, then I have to exponentiate both sides. So this will be equal to e to the minus 1. So the actual result for this infinite product is 1 over e.